Okie dokie. We're gonna go over some of chapter. What was this? Chapter 15. Yeah, we're gonna go over some BIT 2406 chapter 15. Specifically, we're gonna start with time series methods. I'm not gonna talk about this first stuff. You can read over it yourself. Time series methods, starting with the moving average. So moving average is basically just like predicting the next value based on the previous either 3 to 5 values. So, for example, here's a great, representation here. So, in the months January, February, and March, we have these orders, and once it hits April, they're allowed to, forecast the April amount based on the previous 3 months. That is called the 3-month moving average. So you calculate the average again, simply like you're used to calculating averages by adding these 3 values and dividing by 3. And then after 5 months have gone by, you can now predict the 5-month moving average for June because 5 months have already passed by. Like you have information from the previous 5 months. So 5-month moving average would be the average of these 5 values. So you sum these up, divide by 5, get your answer. So that's what all these are in this column here. So basically, say like this one for June, the 3-month moving average would be the average of this, this, and that. And then the 5-month for October would be basically the average of this, 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 and that. Okay, that's pretty much it. Moving average, very simple. Here's some stuff they say about it. Let's see. Longer period, moving averages react more slowly. Trial and error. Moving average does not react well to changes, but it is easy to use and inexpensive, right? So it's very easy to calculate. It's best used when there's like a pretty solid trend going on, as opposed to different seasonal effects and like bumps, spikes, and dips and whatever that was described earlier in this PowerPoint. So good for short-term forecasting. Now, let's talk about exponential smoothing a little bit, and we'll talk about an example. So, exponential smoothing weights recent past data more strongly than distant data. Okay, so there's like simple exponential smoothing. We'll talk about how that's calculated. It's basically just alpha times the demand plus 1 minus alpha times the forecasted value. So demand's like the true value, forecasted is what you've already predicted, right? So yeah, let's keep going. Alpha is usually between 0.10 and 0.5 or 0.50. The determination of the constant alpha is usually judgmental and subjective, so someone just comes up with it and then they use it to forecast future values. So we have this situation. I think I want to explain it just with an Excel file we have here. So for exhibit 15.1, they've chosen the alpha to be 0.5. We will talk about the beta in a moment, but all we're focused on right now are these 2 columns. Okay, and we're talking about just original exponential smoothing. So the forecast for January, we just call it 37 because we don't have any previous information, so they just probably put 37 there for that reason. Now, this is where it starts. So to forecast the February amount, they're using alpha times the previous demand from January plus 1 minus alpha times the previous forecast for January. Okay, so it's in a way it's almost like averaging. It's a weighted average of the previous demand and forecast. Okay, so then it really starts changing once you get to March here, because it's then repeating, right? So it's doing alpha times the 40 plus 1 minus alpha times the forecast, and then it just goes on and on and on. So then this one, for example, the forecast for October is alpha times this plus 1 minus alpha times that. Anyway, it's forecasting. This is the simple exponential smoothing. Then there's an adjusted exponential smoothing forecast, which is, you would hope, I guess it's more accurate. I don't know, 100%. So let's talk about the trend thing. The trend is what uses alpha, if I'm not mistaken. Yeah. So trend shows up at some point in this PowerPoint. Let's see, before we go on to that, let's see what they're talking about here. Both forecasts lag behind, constantly lower. lower constant, smoother data. So here's something interesting. Low smoothing constants, so like the alpha, are appropriate for stable data without trend. Higher constants appropriate for data with trend. So if you have more of a like stable data that's like pretty constant over time, then use a lower alpha. Higher constants, higher alphas are appropriate for datas with trends, like either constantly increasing or constantly decreasing, whatever. Now, adjusted exponential smoothing. This right here. So we're calculating t, which is the trend, and then we use that trend to calculate the adjusted forecast. So this is where the beta comes in. Okay, so let's explain it with the Excel thing here. So say just pick a random point here. We are doing the beta times the difference of C12 minus C11. So what that means is we're doing beta times the difference of the two forecasts. Okay, so previously we had the forecast, we had the prediction for May of 38.38. Now we're like picking up on a trend, and then we will use that to come up with the adjusted forecast for the month of May. So we do beta times the difference of the previous, or like the current and the previous forecast, and then plus 1 minus beta times the trend value. Again, so it's like it's got to use the previous trend value to calculate the new trend. It's a reiterative sort of equation. What is that called? Recursive. Yeah, so that's what it's doing. It's calculating the trend all the way down. So again, beta times the difference of these forecasts, the current minus previous, and then plus 1 minus beta times the previous trend. Then to get the adjusted forecast, you add the simple forecast, the simple exponential smoothing forecast, plus the trend to get the adjusted forecast. That's it. And that's what they're describing here. So you find the trend, then to find the adjusted forecast, you take the previous forecast plus the trend adjustment thing. Okay, so now that we know some of that, the error is always going to be the true value minus the adjusted value, or the forecast value, and this is the adjusted forecast that we're using. So we're considering these two columns, and we're finding the difference in the two. That gives us error. Absolute error is just taking the absolute value of all these errors to get rid of any negatives, basically. Then let's talk about these. Let's see if we can find them in the PowerPoint. And before we do that, let's see if there's any other important information about these. So exponential smoothing, it is more reflective of the generally increasing trend of the data. I believe that's specifically maybe for adjusted forecasts. So like when you have the adjusted exponential smoothing, it's going to be more reflective of the generally increasing trend of the data. Let's see, we'll talk about least squares in a little bit, but I wanted to see the MAD stuff. There it is. So there's something known as mean absolute deviation. So the average absolute difference between the forecast and the actual demand. Very simple calculation if you break it all down like this Excel file has. So they found all the errors, the differences between the actual demand and the forecasted demand. So that was the 41. And I think they just divided it by however many months there were, something like that. So they divided it by 11. Now, is that how many months there were? Probably not. But is that roughly what we're going for? I guess. I don't know. Something along those lines. Okay, so they're averaging. This divided by, maybe it's because there's like 11 jumps. It's like from January to February is a jump. Feb to March jump. I don't know. Something like that, roughly. And then MAPD, that's something with a percentage. There's a chance they just left the 11 there on accident. Maybe that's legit. I don't fucking know. I'm just doing the best I can here with what I have. So, bunch of MADs. Now, mean absolute percent deviation. So MAPD, kind of similar, except we're just dividing by the actual sum of the demands. So when we look at this, notice they're taking the error and dividing it by 520. Now, you could assume, we're going to hope that 520 is meant to be the sum of these values here. It's not. The sum of these values is 557. So, I want to say the 520 came from like, it was an accident. I feel like it came from something else on these slides here. Like this 520, I think, comes from different information. Like it comes from this, which I don't think that's the same as what's going on here, is it? Maybe it is. I don't know. 4756, is that on there? Yeah, maybe it is. I don't know. I might be missing something. But I don't know where they got the 520. It's supposed to be the sum of the demands. That's all I know. So maybe they just started here. Maybe you just don't count January for all these. Maybe that's what it is. Okay, so maybe that makes the 11 make sense. So let's talk about this. So notice there's no like forecast or things here. It's just like they start at February basically. So if we go February to December, that makes the 11 make sense. And then I'm just seeing if we just do the sum, we leave out January and just do the sum of these, we get the 520. Okay, maybe that does make sense. Okay. So anyway, they take the absolute error divided by the 520, multiply by 100. That gives you a percentage, so 8.1%. And then E is just error. That's just the 21.14. Okay, I think that's all I wanted to talk about. Here's something interesting. The lower the value of MAD relative to the magnitude of the data, the more accurate the forecast, which makes a lot of sense because if MAD is mean absolute deviation, how far the predictions, how far the forecasts are deviating from the true value. The lower that is, the more accurate the prediction is, right? Okay. So likewise, the lower the percentage, the more accurate the data. I think that's all I wanted to talk about here. Let's see. Yeah, that's about it. All right. I think I'll make one more video on like the linear approximation stuff, like linear regressions and stuff. So feel free to check that out.